Hello all, welcome back. And in today's session, we are going to explore the details about this circuit. As you can see on your screen, all I have is an amplifier with a gain A, and it is an operational amplifier, very fondly called as op-amp. And it has a positive input, it has a negative input. I am applying a signal, external input signal to the positive, and then to the negative, I am making this connection as shown. And here is your output, which is fade back. So I can also say that my output is making connection with the negative input of the op-amp. Okay. So actually we have understood the theory of this circuit in our previous video, so you might want to explore that. So in today's tutorial, we will see the simulation of this circuit, okay? And we'll run different analysis and we'll see how the response works. Now you see there is a negative pin and the positive pin. These are the supply voltage pins. So to the positive pin, I have applied the positive voltage, which is a separate voltage source right over here. So I have a separate voltage source named as V1. It has a value of DC 12 volt, and its output, it's the positive net V plus, is connected right over here. And how do I ensure whether that connection from here to here is made? I will show you. I am using the circuit simulator. So what I'll do, I will just click the net right here, and you can see that this voltage has been printed also. But I will just do one thing. I am clicking this net, right click with this and click highlight net. So you see the yellow color shows these two, there is a connection between these two pins and these two nets. Okay, so now with that said, how this circuit will work. So I have a positive input. The operational amplifier has a gain A, which is called as open loop gain. Open loop gain, very fondly it's called as AOL, and usually it is in the range of 10 to the power 6 to 10 to the power 7. For a special op-amp, it could be in this range. So how do I ensure this has a value of gain falling in this range? So I right click this, and you can see I have chosen a universal op-amp from the library of the circuit simulator. So it means it is a general purpose op-amp used for every application that I want to build, and it has a feature that I can change. So here value 2, in which I see AVOL, that is 1 mega, that is open circuit open loop voltage gain, which is set to 1 mega. I can change it to, let's say, 10 mega also right over here, but I keep it 1 mega. Then it has a gain bandwidth about 10 mega. So what is gain bandwidth? For an amplifier, there is a gain and there is a frequency in a Bode plot. So the product of gain at that particular frequency, which is a gain bandwidth product, is called as that one. So let me just tell you that. Right, and one more point is the offset voltage of this amplifier VOS is set to 0 here. So it is an ideal op-amp in which I see that I don't need to apply any offset voltage between the two terminals of the op-amp, that is positive and negative, to nullify the output to 0. In practical op-amps, you offset voltage is the one that needs to be applied between the two terminals of the op-amp right here across the two, because operational amplifier is essentially a differential amplifier, and that offset voltage will make sure your output is 0. So with that said, I just told you why I use the universal op-amp, because I can set my own gain. I can set my own gain bandwidth product, and I can set an offset voltage, which is given set to be 0 in this case. Now, how this circuit works, that's the main question here. So you see, to the positive input, I have this input signal that is coming. It could be a DC voltage or it could be an AC voltage. And I know that the output of the op amp, V out divided by V in, is actually my gain. That is the gain of the op amp. And we know that it can also be written as V out, and V in is basically VID. I would say V in is equal to VID, and VID is like this, and that is equal to this one. Okay, now what is VID? VID is the difference between the two voltages, positive and the negative. So I will say, let's say I call it as V1, I call it as V2, and V out divided by V1 minus V2 is equal to A. Now what is V1? I would write V out divided by V in, which is this voltage. And what is V2? V2 is essentially the output only, right? This is V out is equal to A. Now, what I want to say here, usually we say that the open loop gain of the amplifier is very high, 10 to the power 6 to 10 to the power 7. Ideally, AOL is equal to infinity. And amplifier, the function of the op amp is that it is a difference amplifier. So it will amplify the difference between V1 and V2 and nothing else. It doesn't amplify the individual signal, rather it amplifies the difference. And that is how we say that V out is equal to A times VID. Okay. So if because the gain is infinite, ideally, we say that if we look at this equation, if the gain is infinity, then V1 has to be equal to V2 because their difference would be 0. Only when the difference between the two inputs V1 and V2 is equal to 0, gain tends to infinity. Okay. So with that principle, this voltage applied at V1, which is V in, comes here. Okay, because if V1 and V2 are same, then only this condition is met and it tends to infinity. Now, in our practical situation, gain is not infinity, but it is still very large, 10 to the power 6 to 10 to the power 7. So because of this very high gain, this voltage at the positive input, which is V1 equal to V in, will try to match or will try to come at this negative input. Then V2 will also be equal to V in, right? Or V2 will try to catch up with V in essentially. And this V2 is nothing but your voltage at the output. So if your gain tends to be very large, I would not say infinity. I would prefer writing it is very large, then V1 is equal to V2, and therefore V out is equal to V in. Essentially, you see this voltage is coming here and then it is coming here. So V out is equal to V in. Therefore, this circuit, therefore, the circuit is called as voltage follower. Voltage follower. Okay. It is also called as an buffer circuit. Because when it is called as buffer circuit, what it has is it has a very high R in is equal to infinity ideally, and R out output impedance is equal to 0 if this is a buffer, a voltage follower. So Rin is equal to infinity. It means it offers a very, very high or ideally infinite input resistance. It means the circuit, you can have another circuit's output if it has very low current capability to drive, then this circuit can be driven by the circuit at the beginning. And it has an output impedance equal to 0. It means it has a very large current driving capability. It has a possibility to drive loads which has a requirement of high currents. So that's its use, the buffer. So now we have done this analysis, theoretical analysis. We know that how the circuit is working and why it is called as voltage follower or buffer. How about we run an analysis of this circuit? So let's say I have used the 12-volt DC for the operational amplifier power supply. That is the case. But now I want to understand when I run the analysis, what are going to be the voltages and the current. So what I'll do, I will first cancel it. Forget about, I have currently used this sinusoidal voltage source that I will show you later. First, I will click none, here none, and I will put the DC value of this voltage source. Let's say I use a 1 volt at the input, right? And let me drag this value to its voltage source. And then the voltage at the positive input now is 1 volt, and the voltage at the negative input has to be 1 volt because of the theory we just explained, and therefore output has to be also 1 volt nearly. We'll see whether it behaves exactly what we just saw. So for that, I will run the operating point analysis, which is currently disabled here because I had run the transient analysis that I'm going to show you again. But before that, we'll run just DC analysis to see the voltages and the current. So what I'll do, I'll just right click here. With that, I will enable this with this command, and I will disable this transient analysis because I can run one analysis at a time. So I will do that. So you see .dc and .transient analysis has been disabled. So let me just click run. Okay, with this now, you see at the node voltage 001, I have 1 volt. Now, what is that node voltage 1? Let me clear the drawing for your better understanding. This will make you understand things clearly. Okay. Right here, we see that. Now, why there is this question mark, we have to figure out. We'll do that later, but circuit is okay. There is no error. So at node, voltage at the node 001 is 1 volt. So this is most probably this node. Not most probably, definitely this is the 1 volt. Then voltage at the V plus, which is 12 volt right over here, which is the supply rail of the op-amp. Now voltage at the output, you see 0.99. There is a difference between 0.11 only, right? So its output follows input. And there is a current from the source, which is about 10 nanoampere. Then the current from the power supply rail is about minus 22 nanoampere, and that's it. So we got this analysis. So we see that. How about I sweep the DC voltage, let's say from 0 volt to 10 volt, and we'll see if the amplifier's output follows that one. So for that, I will re-enable this DC analysis. And I am here sweeping this DC voltage source from 0 to 5, or let's say 0 to 5 is okay, and at the step of 1 volt. So it will start from 0, 1, 2, up to 5 because the steps are 1 volt. So I will just click OK. And then I have done this. But now .op analysis has to be disabled, or I can let it compute that as well. Click run here. That's it. So you see now I have waveform viewer open. On the schematic, as soon as I move the mouse near the net, I get this red probe enable that is asking me to plot the signals. So I click and I have a linear increase of input voltage at the positive input of op amp starting from 0 and it goes to 5 volt. Now what I want, voltage at the negative input because of the very high gain of the op amp. Again, let me explain to you. Because of the very high gain of the op amp, we have set it to be 1 to the power 6, okay? Because it's a universal op amp. Remember that? In the properties, you right click and see what is the property. So it is AOL, very high gain. So I will now see whether the voltage at the negative input of op amp follows the voltage at the positive because of the high gain. So click here, right here, good. You see the blue line superimposes the green line, and voltage at the negative input is nothing but my output voltage. You see this net is common here, right here. So that's why the here I see the V out. Okay, I can just use a different color. For example, for this, let's say I use the red and click OK, and that's it. I can also separate, add plot pane. V in should be up and V out. So you see exactly output is following the input. And that's how this circuit is called as voltage follower. How about I made some adjustment? Let's say I keep it on the same. I delete this pane. And now it is on the same. V out follows input because again the gain is pretty high. What about I right click the op amp and change the gain from 1 mega to, let's say, 1000 only. Will that make any difference? We'll see. Now the gain has been lowered by 2 orders of magnitude. So just click here. It still follows your input because of that. 1000 it seems, but how about I just have 100? We'll see that. Now you see there is a little difference that is coming right here. The gain is not exactly 1, right? The gain of this circuit is 1 because output is equal to input. Now there is a disparity between output and input. Output is lower than the input. You can clearly see that this is the effect of lowering the gain. Again, right click. Let's say I have 10 ohm. 10 only. Gain is open loop, gain is 10. And save, and now click run. So you see there is the red line, which is an output, is no longer following your input voltage. So it's a very good example about manipulating your circuits and see the impact of varying various parameters. So that's how you're becoming a good designer, right? So no longer is the case. So you have to have a very high gain. Let's say keep it back about 1 mega, 1 e to the power 6. Now the gain bandwidth product is 10 mega. It will come back again normal. Okay, good. How about reducing the bandwidth of the op amp? But we don't have any AC signal. We'll do that when we apply a sinusoidal or time varying input. Now we are playing with DC. How about offset? Let's say offset is 0. But I have used, let's say, 1 e to the power minus 3, 1 millivolt offset. And there is another also, input impedance is 500 mega ohm, which is pretty high. There is a bias current, input IN equal to 0, INK equal to 0, right? And this is EN equal to 0, ENK is equal to 0. So you have to understand what's the meaning of that by referring to the SPICE model. So for now, I have changed the offset to the 1 millivolt. Click OK. Now let's see the impact. No impact. I have still a good voltage follower. What about I keep it, let's say 10 millivolt, and I run. I see the difference, little bit difference has come here. I see that it is no longer a little bit drop, right? So that's very good. Now I see that I use it like, let's say 100 millivolt. It's pretty good. So now it's clearly a voltage follower, no longer exact voltage follower. So in practical op-amp, when you will build the circuits, you will have such situations, right? Your input is not equal to output is not equal to exactly input. So keep back, go back and keep it like what it was, 0, right here, and then click here. And that's good, right? So what about now changing the input impedance? It's 500 mega, so differential amplifier has infinite input impedance, and ideally, practically, it is very high. How about I keep it to, let's say, 5,000? That's it. 5,000 still be bigger, but how about yeah, 5,000? Let's keep. We'll go step by step. Click OK. Run. No difference. Again, right click. How about I choose it to be 500? Click OK. OK, and then no difference. So it's like it's still working fine with the 500. How about 50? And then let's say, yeah, so there is no difference between the input impedance of the amplifier. So it was like 500 mega. So keep it that way. Or maybe just say 500 mega. Yeah. Okay. So now you see that we have seen how the circuit is working for the DC inputs. How about we just do some, instead of DC input, we change it to sinusoidal input, and we'll see if it works. Let's say DC offset is 0, ideally. Amplitude is 1 volt. Frequency is 1 to the power 3. Delay and theta and phi, we don't care. And then number of cycle 10. And we'll run the analysis. So now you have this sine wave at the positive input of the amplifier. Now I need to run the transient analysis. So what I'm doing here, I'm disabling this DC analysis, or right now I will just enable this analysis. Right click. This is the syntax of the transient analysis, like dot tran. I am starting from 0 seconds going to 50 milliseconds, and stop time at the step of I don't have any steps right here. So I click OK, and as soon as I click OK, this analysis got enabled. But before running that, I have to disable this analysis, the DC. So I will just put this symbol and click OK. It is disabled. Now it is good. So click here, and now you can see that for the 10 cycles, my green line is the input and the red one is an output. So it is very closely following the input. So that's exactly is the voltage follower for the 10. So why not I just run it for 10 milliseconds instead of 50? I will just keep it like 10. Click OK and then run again, and you see now. So that's very obvious. How about now again, we can run same things what we did with the DC analysis. How about reducing the gain to just 10 and click OK and run. So you now see the green is the input, but the output is still manageable, but it's not exactly the voltage follower. It is pretty, there is a difference. You see the output is lower than the input. So that's the impact of it. So just click schematic window, then click edit, press F9, which is undo. So your gain is preset to 1 mega. How about gain bandwidth product? So gain bandwidth product is 10 mega or 10 mega actually. So it's the multiplication between gain and the bandwidth. So tell me now, if the gain is 1 mega and gain bandwidth is 10 mega, what is the pole frequency of this amplifier? Let me write it for you. We'll calculate that. Because you are using a op-amp, so it's an amplifier, so it has a response, frequency response from the body plot like this. So this is your, let's say, gain. This is your frequency, and this is about your minus 3 dB point, from where the gain starts dropping like minus 20 dB per decade, minus 20 dB per decade. Okay, so I just said OAL is your 1 e to the power c, and the gain bandwidth is about 10 to the power 6, and gain bandwidth is your AOL multiplied by your frequency. Yeah, your bandwidth of the amplifier, or a frequency. So frequency would be gain bandwidth product divided by AOL. Will it be like this? So it would be like 10 e to the power 6 divided by AOL, which is 1 e to the power 6. Will it be only 10? We'll see that 10 hertz. Yeah, it will be 10 hertz. So it would be like in an open loop, your frequency would be 10 hertz. We'll see that. So no, it won't be 10 hertz. We have to figure that out. Let me check that out. Just a minute. Okay, we'll do that later. We'll explore this point about gain bandwidth product and the gain and the frequency. We'll explore that relation later. So right now we are applying 1 kilohertz sine wave, and we are running the transient simulation, and we are seeing that it exactly acts as a voltage follower. How about I increase the frequency to, let's say, 10 kilo or 100 kilohertz, and we'll see that how it goes. Now 100 kilohertz means I have to run simulation about in 100 microseconds, something like that. So it's still pretty closely following the input. The output is following the input. How about I have 1 mega, 1000 kilohertz is about 1 mega, because that's how I do it. Now it is like I have to run about 10 micro, run it. That's okay. Now you can see still there is a little phase difference, that output is still, we can say that it is a voltage follower. Okay, but now how about I change this? Gain bandwidth is 10 mega, I keep it 1 mega, just here. So now you will see the output has dropped. So that's the maximum frequency your circuit can work. That's the maximum gain bandwidth your circuit can work with. Okay. Because you are applying 1 mega, and now your gain bandwidth is 1 mega. So you have to tell me why your output failed down. Okay. So that's it. How about I decrease the frequency of it? Instead of 1 mega, I will use 100 kilohertz. So 0.1 mega. And now we'll see. Yeah, so it's okay. Now it is following the output is following the input. There is no question about that. Is it? Let's run it for a little longer time. Let's say about 100. And yeah, it's no problem. So keep it that way. This is like 10 meg. Good. So you have to tell me in the comment section why, if I increase the frequency, let's say about 10 mega, for example, here, or I decrease the gain bandwidth of the op amp, why the output doesn't follow the input. Now you see, up to 1 mega, it's just following. Other times, it's not. So there is a relationship between gain bandwidth and the frequency of the operational amplifier, the maximum frequency, that is the speed. Okay, so let's come back here. This is okay, 10 mega. But if I keep it 100 mega here, if I make it 100 mega, then the output should be back following the input. So perfectly, there is no issue with that. You see, there's no issue with that. Okay, so now we are done with the DC analysis, DC sweep, transient. How about last and final AC analysis? And there are many other analysis we can done. So let's do that. So let's disable this transient analysis with this symbol. Click OK. Now I will change the source to back to the AC, small signal AC analysis right here. So I will keep the amplitude to be 1, and I'm essentially going to plot the Bode plot. So is AC right here, and I don't need .op also, or maybe I just keep it like this. Now I want to run the AC analysis. So I click simulate, edit simulation command, and here I choose AC. Type of sweep is decade. Number of points, let's say 2000, start frequency 1 hertz, stop frequency, let's say 1 mega. Click OK. And here, that's it. Once that is done, click run. And pretty good. We are actually interested in the output only. So I delete the input press. And you see now, I have a gain about 0 dB minus point micro dB. So it's essentially it is close to 0 dB because gain is 1, and gain is 1 till your gain is 1 till this frequency minus 3 dB point, minus 3 dB point. So at about 1 mega, this is like 200 kilohertz. This is 300 kilohertz. Minus 3 dB point is not that one. It's still is a long one. So we have to run the analysis for a longer frequency. So let me just run it for let's say 100 mega. That's how we'll get the 3 dB point run. So here is minus 3 dB point right here. Right here, because you see on the y-axis you have minus 3 dB point. So right here, I see that frequency 200, 300, 400 is about 1 megahertz. So that's my minus 3 dB point, not this one. Okay, let me erase that. Let me erase that right here. And this is minus 3 dB point. Minus 3 dB at approximately 1 e to the power 6 hertz. And at this frequency, gain is no longer 1, because voltage follower means VO over V in is equal to 1. This is the closed loop gain. Okay, and this is possible because of your open loop gain, which is A, or let's say AOL, which is 10 to the power 6. So because your open loop gain is very high in the range 10 to the power 6, you have a closed loop gain approaching 1. So that's the comprehensive understanding about the voltage follower or a buffer circuit. Hope you like this video. If you did so, click the like button, comment on it. I have given you an exercise about finding the relationship between gain, bandwidth, and the frequency or the speed of the op-amp, and then subscribe to the channel, share it with others for a wider reach, and wish you happy learning. Stay tuned for more informative content like this.